Imagine you just place a red billiard ball and a blue billiard ball on an empty table.
Just a perfectly normal flat table.
Right. And in our everyday experience, they just sit there, nothing happens.
Right, classical physics at work.
Exactly. But in the extreme frontiers of theoretical physics, something genuinely terrifying happens. The blue ball pulls the red ball closer, but the red ball fiercely pushes the blue ball away.
So instead of colliding,
They start chasing each other. They literally accelerate across the table, moving faster and faster, approaching the speed of light.
and they do this forever.
Right, forever, without any fuel. And all the while, the total energy of this bizarre system remains at exactly zero. Today, we're looking at the math that says this shouldn't just be possible, it might actually be the secret to the entire universe.
It is a profound paradox, honestly, and it sits right at the very edge of what we understand about reality. Because when you push the equations of general relativity and quantum mechanics to their absolute breaking points, the universe, it stops playing by those comforting, predictable rules we learn in grade school.
Which is exactly why we are here.
Yeah.
Welcome to this deep dive. If you are listening to this, you are a fellow curious mind. We know the daily grind is loud and demanding and just overwhelming.
It really is.
So we invite you to just sit back, take a slow breath, and let your mind drift with us for a while. Think of this as a late-night, fireside intellectual chat.
Yeah.
We are dimming the lights on the everyday world and turning our focus outward, to the most hidden, counterintuitive corners of reality.
There's a really unique kind of peace to be found in contemplating the profound mysteries of the cosmos, stepping away from our immediate, tangible stressors to look at the massive, intricate machinery of space-time. It puts everything into a rather beautiful perspective.
I completely agree. And our mission for this deep dive is to map that machinery. Today, we are decoding the dark.
I love that framing.
Yeah, we have a fascinating stack of cutting-edge physics papers, theoretical propositions, and recent experimental results. And we're going to translate them into a relaxing journey through the invisible forces that shape our universe.
We're going to cover a lot of ground today.
We really are. We are exploring the physical reality of antimatter, the chaotic mathematical thread of negative mass, the quantum rule breaking of the vacuum, and the deeply paradoxical interiors of black holes.
The sources we are drawing from are incredibly rich, too. We will be analyzing the recent ALPHAG experiment at CERN, wading into the heavy theoretical frameworks of general relativity's energy conditions, unpacking the quantum holographic principle, and finally looking at a highly radical biometric cosmological model.
So we are traveling from the tangibly verified to the absolute bleeding edge of theoretical mathematics. But before we can explore that runaway billiard ball scenario, which deals with the purely hypothetical concept of negative mass, we first need to clear up a massive cultural misconception.
Oh, the science fiction issue.
Right. Science fiction has completely conflated negative mass with antimatter. So let's anchor ourselves in reality first. Antimatter isn't just a theory, we create it. But what exactly is it structurally?
Well, to understand antimatter, it really helps to look at the brilliant mathematical leap of faith taken by physicist Paul Dirac in 1928. He was trying to write an equation that combined quantum mechanics with Einstein's special relativity to describe the electron.
Okay.
And his beautifully elegant equation worked. But it yielded two solutions, one for positive energy and one for negative energy.
Kind of like how taking the square root of 4 gives you both a positive 2 and a negative 2.
Precisely the same mathematical principle, and most physicists at the time looked at that negative solution and dismissed it as a purely mathematical artifact, just physical nonsense.
They just ignored it.
Right. But Dirac took the math seriously. He proposed an incredible idea called the Dirac sea. He suggested that the vacuum of space isn't empty at all. It is filled with an infinite sea of electrons occupying negative energy states.
An infinite sea.
Yeah, and because the sea is completely full, we don't notice it. It's just the background canvas of the universe.
But if you poke a hole in that canvas.
Exactly. If you inject enough energy to knock a negative energy electron out of the sea and into our positive energy world, it leaves behind a hole in the vacuum.
Wow.
Dirac realized that this hole would act exactly like a particle. It would have the exact same mass as the electron, but because it's a missing negative charge, it would behave as if it had a positive charge.
It's like a bubble in a sea of negative energy. That is a gorgeous way to visualize it. So this missing hole, this bubble, is the positron. the antimatter twin of the electron.
And that mathematical leap gave us the physical reality of antimatter. An antiproton is just the antimatter twin of a proton's same mass, but a negative charge. Antimatter is, essentially, normal matter with its electrical charge reversed.
Which brings us to the sci-fi myth we need to bust. Because their charges are reversed, a lot of pop culture assumes their interaction with gravity is also reversed.
The anti-gravity idea.
Right, the idea that antimatter possesses anti-gravity properties, that it would just float up into the sky if you dropped it.
It's a persistent myth, and one that the physics community desperately needed to test empirically. Not because we genuinely believed antimatter fell up, but because if it did, it would completely break Einstein's general theory of relativity.
That's a huge deal.
It is. And that brings us to the landmark ALPHAG experiment conducted at CERN, with results published in late 2023.
The methodology of this experiment is staggering to me, because you can't just put a block of antimatter on a scale.
No, definitely not.
The moment antimatter touches normal matter, like the scale, the air, the walls of the room, it just annihilates.
It converts entirely into pure energy, obeying Einstein's E = mc squared. It is a perfect violent conversion. So the ALPHAG collaboration had to perform an absolute miracle of engineering.
What do they do?
Well, they couldn't use charged particles like positrons or antiprotons because the electromagnetic forces would completely overwhelm the incredibly weak force of gravity. They needed a neutral atom.
Oh, so they had to actually build antihydrogen.
Exactly. They took antiprotons from a particle decelerator, slowed them down to a crawl, and mixed them with a perfectly chilled cloud of positrons. When the conditions were just right, the positrons began orbiting the antiprotons, synthesizing cold, neutral antihydrogen atoms.
But they still have the annihilation problem, right? The antihydrogen is neutral now, but if it drifts and hits the metal wall of the vacuum chamber, it's gone.
Gone instantly. So they built a magnetic bottle using deeply complex superconducting magnetic fields. They trapped these delicate antihydrogen atoms in a pure vacuum, suspending them so they touched absolutely nothing.
Incredible.
The ALPHAG apparatus is essentially a tall, vertical shaft. To test gravity, they simply held the antihydrogen in the middle of the shaft and slowly, carefully ramped down the magnetic fields, holding them at the top and bottom.
The ultimate drop test.
The ultimate drop test. They watched to see where the annihilation flashes occurred. If antimatter had anti-gravity, the flashes would cluster at the top of the shaft as the atoms escaped upward.
And if it obeyed normal gravity, the flashes would cluster at the bottom.
Oh, whoa.
The flashes clustered at the bottom. Antimatter embraces the Earth. It falls downward, exactly like an apple falling from a tree.
It falls with the exact same acceleration, too. Antimatter has positive inertial mass and positive gravitational mass. The Dirac sea bubble still responds to the curvature of spacetime exactly like the water around it.
Okay, let's unpack this, because that result is a massive relief for physicists. It preserves Einstein's equivalence principle, the bedrock idea that gravitational mass and inertial mass are the exact same thing.
Thank goodness.
Right, but for our journey decoding the dark, it acts as a critical pivot point. If antimatter isn't the exotic reality-breaking stuff we thought it was, where does the real weirdness actually live?
It lives in the concept we touched on at the very beginning, the runaway billiard balls. We have to leave the physically verified realm of antimatter and wade into the mathematically possible but philosophically terrifying waters of true negative mass.
Let's set the table for this. In our everyday world, if you push something, it moves away from you. That is positive inertial mass. Newton's force equals mass times acceleration.
Right.
And if you have a massive object, like a planet, it pulls things toward it. That is positive active gravitational mass.
And under Einstein's equivalence principle, those masses are identical. So theoretically, what happens if we plug a true negative number into Einstein's field equations? A mass of less than 0.
Does the math just crash?
It doesn't crash. It computes a spacetime geometry. But the implications of that geometry are what physicist William Bonner famously called preposterous.
Because it creates the Bondi runaway motion paradox. Let's look at those billiard balls again, but through the lens of gravitational fields. We have the blue ball, which is normal, positive mass. It creates a standard gravity well. It pulls things in.
And then you have the red ball, which is negative mass. Because its active gravitational mass is negative, it doesn't bend space-time down into a well. It bends space-time up into a gravity hill. It repels everything around it.
Okay, so if I place them near each other, the blue ball's gravity well tries to pull the red ball closer.
Yes, the blue ball actively attracts the red ball. The red ball feels that pull and falls toward the blue ball.
But the red ball's gravity hill is actively pushing the blue ball away.
Precisely. The blue ball is attracted to the red ball, so it moves toward it. The red ball is repelled by the blue ball, so it moves away from it. The red ball chases the blue ball.
This is just so weird.
Or rather, the negative mass pushes the positive mass away, while the positive mass violently drags the negative mass along behind it.
And because gravity's influence extends infinitely, they never escape each other. They just lock into this bizarre chase, accelerating infinitely in the same direction.
They will accelerate together indefinitely, approaching the speed of light.
Here's where it gets really interesting, and I have to push back here, because my brain is screaming that this violates the most sacred rule of physics, the conservation of energy. You can't just have two objects accelerating forever without an engine, without burning fuel. Where is the energy coming from?
That is the most brilliantly counterintuitive part of the paradox. In 1990, the physicist Robert Forward mathematically proved that this runaway motion is completely perfectly consistent with the conservation of energy and momentum.
Wait, really? How is that possible? They're gaining speed.
They are gaining speed, but look at the mass. Kinetic energy is 1/2 mass times velocity squared. As the positive blue ball accelerates, its positive kinetic energy skyrockets.
Okay, that makes sense.
But as the negative red ball accelerates, because its mass is negative, its kinetic energy becomes deeply, massively negative.
Oh, wow. I see. Positive 1 million joules of energy for the blue ball, and negative 1 million joules of energy for the red ball.
Exactly. When you add them together, the total energy of the system remains at exactly 0. The same goes for momentum. The positive momentum of the blue ball perfectly cancels out the negative momentum of the red ball.
That's wild.
They can accelerate forever, and the universe's accounting ledger remains perfectly balanced at 0.
That is a staggering loophole in the laws of physics. But if the math works, and the conservation laws are preserved, why do physicists universally reject it? Why do we ban negative mass from our classical models?
Well, because if negative mass existed freely, empty space itself would be fundamentally unstable. Think about it. If the total energy cost of creating a positive mass and a negative mass together is 0, then a completely empty vacuum could spontaneously generate pairs of these chasing billiard balls out of absolutely nothing.
The universe would just instantly fill up with infinite light-speed pairs of particles tearing through space.
The vacuum would decay into pure chaos. So to prevent this, physicists constructed mathematical guardrails. They couldn't just put a sticky note on Einstein's equations that said, please only use positive numbers. They had to formalize it.
They created the energy conditions.
Yes. The energy conditions are locally defined rules imposed on the stress-energy tensor. That's the mathematical object that describes the density and flux of energy and momentum in space-time. They are essentially a mathematical gentleman's agreement to keep classical physics safe, predictable, and free from runaway paradoxes and time machines.
Our sources highlight 4 specific classical energy conditions. Let's walk through them, because they are the structural pillars we are about to knock down.
The first and most foundational is the weak energy condition, or WEC. It states a very simple rule. The energy density measured by any observer traveling slower than light, what we call a time-like observer, must always be positive or 0. You can never, under any circumstances, measure a negative energy density.
Right, and that directly bans our red billiard ball.
Outright. The second guardrail is the null energy condition, or NEC. This is similar, but it applies to light. It states that the energy density measured along the path of a photon, a light-like or null vector, must be positive or 0.
So no matter how fast you are going, even if you are a beam of light, you cannot encounter a pocket of negative energy.
Correct. Now, the third rule, the strong energy condition, or SEC, is fascinating because it dictates the focusing behavior of gravity. It mathematically ensures that gravity is always an attractive force.
Okay.
It states that the gravitational pull of matter must cause the paths of freely falling objects to converge, to pull together.
But wait a second, if we look out into the cosmos, we know the expansion of the universe is accelerating. Galaxies are being pushed apart. Doesn't that mean their paths are diverging?
Yes, and that is a brilliant observation. The physical reality of dark energy, or the cosmological constant, actually violates the strong energy condition on a cosmic scale. Dark energy acts as a repulsive pressure, driving the universe apart. So the SEC is a guardrail that nature has already happily smashed through.
Nature doesn't care about our gentleman's agreement. What about the fourth rule?
The dominant energy condition, or DEC. This rule ensures causality. It states that not only must energy density be positive, but energy cannot flow faster than the speed of light. It guarantees that cause always precedes effect.
So these four rules, the WEC, NEC, SEC, and DC, they are the firewall. They keep space-time geometry stable, they prevent wormholes from being propped open, they stop time machines, and they banish negative mass.
In a purely classical universe, yes. If those conditions hold, the geometry of the universe is safe. But classical physics is only half the story. When we zoom into the incredibly microscopic subatomic level, the universe stops caring about classical geometry.
We enter the quantum rebellion.
We do, because quantum field theory doesn't just bend the energy conditions, it actively violently shatters them. It generates the very exotic negative energy that classical physics tried so desperately to ban.
Let's slow down and really look at this mechanism, because the idea that negative energy is real is hard to wrap your head around. How does quantum mechanics produce something less than nothing?
Through a phenomenon called the Casimir effect. And I want to stress, this isn't a chalkboard theory. This is a fully experimentally verified physical reality.
Walk us through the experiment.
Imagine two perfectly conducting, uncharged metallic plates. You place them parallel to each other inside an absolute perfect vacuum chamber. You bring them incredibly close together, just a few nanometers apart. Now, classical physics tells us that because the plates are uncharged and the space between them is a total vacuum, there are no forces at play. Nothing should happen.
But we know from the Dirac sea that a vacuum is never truly empty.
Exactly. Quantum field theory reveals that a vacuum is a boiling, chaotic sea of quantum fluctuations. Virtual particles are constantly popping into and out of existence, creating electromagnetic waves of every conceivable wavelength. It is a storm of ambient background energy, often called zero-point energy.
So outside the plates, in the vast empty space of the chamber, you have this storm. Waves of every size crashing around.
But the space between the plates is a restricted zone. Because the plates are conducting boundaries, quantum mechanics dictates that only waves with wavelengths that perfectly fit between the plates can exist there. The wave has to hit exactly zero at the metallic boundary.
So any wave that is larger than the gap between the plates simply cannot exist in that space. It's filtered out.
Precisely. You have an infinite number of waves raging on the outside, pushing inward on the plates, but you have a restricted, highly limited number of waves on the inside, pushing outward. The result is a net inward pressure. The plates are literally pushed together by the quantum vacuum.
That is mind-blowing. The empty space outside is heavier than the empty space inside. But how does that translate to negative energy?
It's a matter of the baseline. If we define the normal unrestricted vacuum outside the plates as having an energy level of exactly zero, then the region between the plates, which has mathematically fewer fluctuations, must have an energy level less than zero.
Less than zero.
By restricting the quantum modes, we have engineered a localized pocket of true negative energy density. And by doing so, the Casimir effect experimentally violates all of the point-wise classical energy conditions we just discussed. It violates the WEC, the NEC, and the DEC. Between those two metallic plates, the strict classical guardrails of general relativity are completely suspended.
If we take that a step further, the implications are staggering. If quantum mechanics is sitting here freely generating negative energy, why is the universe still stable? Why hasn't the vacuum decayed into runaway billiard balls? If I can make negative energy between two tiny plates, why can't I scale it up, build a giant Casimir machine, create a massive gravity hill, and prop open a traversable wormhole to the Andromeda galaxy?
That was the exact panic that gripped theoretical physicists. If the local rules of spacetime are broken by quantum mechanics, how does the global macrostructure of the universe survive? The answer they found is one of the most beautiful compromises in modern physics. It is called the average null energy condition, or ANEC.
Averaged, meaning the universe doesn't care about a single point, it cares about the whole picture.
Exactly. The strict classical point-wise conditions said energy can never be negative anywhere, ever. The average null energy condition says something much more forgiving. It says, okay, quantum mechanics, you are allowed to have a little bit of negative energy in a localized restricted pocket. But if a beam of light travels along a complete unbroken path through space-time from one side of the universe to the other, the total integrated energy it encounters along that entire infinite journey must sum up to a positive number.
So it's like the universe operates with overdraft protection.
Explain how you mean that.
Well, the classical rules, the weak energy condition, that was like a strict debit card. The absolute moment your bank account hit zero, your card is violently declined. You can never hold a negative balance. But the quantum universe is a bit more flexible. Nature is a bank manager that offers overdraft protection. It says, look, I'll let you dip into a negative energy balance for a short period. You can have your little Casimir gap. But eventually, a massive deposit has to be made. Your overall long-term average balance over the course of the journey must remain positive, or I'm closing the account and collapsing the geometry.
That is a phenomenal analogy. And nature, as a bank manager, is incredibly strict about the repayment schedule. The mathematics of ANEC show that the deeper your quantum negative energy debt is, the faster you have to pay it back with an even larger region of positive energy.
So how does this overdraft protection physically stop me from building a time machine or a traversable wormhole?
Through a rigorous mathematical proof called topological censorship. In our sources, it's formally detailed as Theorem 2.6.8. Let's run a thought experiment. Suppose a highly advanced civilization manages to generate an enormous amount of localized quantum negative energy. They use it to tear a hole in space-time, creating a wormhole, a topological handle connecting two distant points in the universe.
They use the negative energy's gravity hill to push the walls of the wormhole apart, keeping the throat from collapsing under its own weight.
Exactly. Now, topological censorship asks a critical question. Can an observer actually send a probe rocket through that wormhole and have it emerge in the distant universe?
Can they?
No, because for the probe rocket to travel completely through the wormhole, the light rays guiding its path would have to undergo a specific geometric transition. As the light enters the wormhole, the gravity is pulling it in, so the light rays converge. They have a negative expansion.
Like a magnifying glass focusing sunlight to a point.
Yes. But to come out the other side of the wormhole and re-enter the normal universe, those light rays must stop converging and begin to diverge. They must spread outward.
So the space-time lens has to flip from converging to diverging.
Sure. And in general relativity, the only way to make light rays stop converging and begin diverging is to pass them through an overwhelming concentration of negative energy. Topological censorship proves that any such trip through a non-trivial topological handle would require so much negative energy that it would permanently violate the average null energy condition.
The light ray would hit the end of its journey, and the bank manager would look at the ledger and realize the account is permanently overdrawn.
And because nature never allows the ANEC to be violated globally, the wormhole must inevitably collapse before the probe rocket can make it through. Nature actively censors exotic topologies. You can have your tiny quantum overdrafts, but the macro structure of the universe rigorously enforces the average positive energy rule, slamming the door on traversable wormholes and time machines.
This realization completely shifts how we have to think about reality. It implies that the large-scale geometric rules of space-time are fundamentally inextricably tied to the microscopic quantum states of the energy residing within it. Geometry is actively policing quantum information.
Building on that, this realization forced a profound paradigm shift. Physicists understood that they could no longer study gravity and quantum mechanics in isolation. They had to find a mathematical language that directly translated quantum information into space-time geometry.
Which brings us to the ultimate arena where gravity and quantum mechanics are forced into a cage match: the black hole.
The densest, most mysterious object in the universe. A place where gravity is so strong that classical physics predicts a singularity of infinite density and an event horizon from which not even light can escape.
But the moment we apply the quantum overdraft rules to the event horizon, the black hole stops being entirely black. Stephen Hawking threw the first punch in this cage match, didn't he?
He did. In the 1970s, Stephen Hawking decided to apply quantum field theory, that boiling sea of virtual particles we talked about with the Casimir effect, to the extreme curved spacetime right at the boundary of a black hole's event horizon. And his calculations revealed something that shocked the physics community. Black holes evaporate.
Let's unpack the mechanism of Hawking radiation, because it relies heavily on that negative energy concept.
Imagine the event horizon. It is a razor-thin boundary, the absolute point of no return. The vacuum of space right on that boundary is still a storm of quantum fluctuations. Pairs of virtual particles, matter and antimatter, like an electron and a positron, are constantly popping into existence. Normally, they immediately attract each other, annihilate, and vanish back into the vacuum, returning the borrowed energy.
But if they pop into existence right, straddling that razor's edge,
the immense tidal forces of the black hole's gravity pull them apart before they have a chance to annihilate. One particle gets sucked past the event horizon, falling into the black hole. The other particle is left stranded outside, and it is forcefully ejected into space.
the ejected particle becomes Hawking radiation. But how does that cause the black hole to evaporate? Doesn't the black hole just absorb the particle that fell in and gain mass?
This is where energy conservation forces our hand. For the escaping particle to become real and fly away, it must have positive energy. But the virtual pair was created from zero total energy. Therefore, to balance the ledger, the particle that falls into the black hole must, from the perspective of the outside universe, carry negative energy.
So it acts like a red billiard ball. When the negative energy particle falls into the black hole, it subtracts from the black hole's total mass.
Exactly. The black hole emits positive thermal radiation outward and ingests a steady diet of quantum negative energy inward. Very slowly, over trillions of years, the black hole will lose all its mass and evaporate entirely into a flash of light.
It is a beautifully elegant mechanism. So why did it plunge physics into a decades-long crisis? Why is it called the black hole information paradox?
Because of a sacred, non-negotiable rule in quantum mechanics called unitarity. Unitarity essentially dictates that quantum information can never, ever be destroyed. The universe must always keep a perfect record of the past. If you possess the complete quantum state of a system, you must be able to run the math backward to see exactly how it started, or run it forward to see exactly where it will end up.
I've heard the book burning analogy for this. In our classical world, if I burn a diary, the information feels lost. It's just ash and smoke. But in a quantum universe, if a supercomputer could track the exact trajectory of every single photon of heat, every molecule of smoke, and every speck of ash, it could theoretically run the physics in reverse and reassemble the words on the pages of the diary.
The information is scrambled, but it is fundamentally conserved. But Hawking's calculations showed something devastating. The radiation emitted by a black hole is purely thermal. It is completely, utterly random. It depends only on the mass, charge, and spin of the black hole. It contains absolutely zero information about the specific quantum states of the matter that fell in.
So if I throw my highly ordered, information-rich quantum diary into the black hole and wait a few trillion years,
the black hole evaporates away into random, meaningless thermal radiation. The black hole is gone, the diary is gone, and the radiation holds no record that the diary ever existed. The information has been permanently deleted from the universe.
and if unitarity is broken, quantum mechanics entirely falls apart.
It was a profound crisis. It forced physicists to reconsider the very fabric of reality, leading to one of the most radical ideas in modern science, the holographic principle.
Let's slow down and really map this out, because the idea that we live in a hologram sounds like pure science fiction. Where did the idea originate?
It originated with the study of black hole entropy. Entropy is a measure of hidden information or disorder. Physicist Jacob Bekenstein was trying to figure out how much information a black hole could theoretically hide. In classical physics, if you have a filing cabinet, the amount of information it can hold is directly proportional to its 3D volume.
Right, a bigger box holds more files.
But Bekenstein discovered that the entropy of a black hole is not proportional to its 3D volume. It is proportional to its 2D surface area, the exact square footage of the event horizon.
That makes no intuitive sense. That's like saying a giant library can only hold as many books as you can paint onto its exterior walls.
Exactly. It suggested that all the complex 3D information of the star that collapsed to form the black hole and everything that ever fell into it was somehow perfectly encoded on the 2D surface of the event horizon. This realization inspired physicists Gerard Hooft and Leonard Susskind to propose the holographic principle.
The idea that the 3D universe is a projection.
Yes. They proposed that any complete 3D gravitational space, what physicists call the bulk, can be completely mathematically described by a 2D quantum field theory residing on its boundary. Just like a flat 2D holographic piece of plastic encodes all the information needed to project a fully 3D image.
But that was just a hypothesis, right? Did they ever prove it mathematically?
In 1997, string theorist Juan Maldacena published a paper that broke the physics world wide open. He proved the ADS-CFT correspondence. It sounds intimidating, but it's essentially a mathematical dictionary.
How does the dictionary work?
He took a specific kind of 3D space called anti-de Sitter space, or ADS. It's a universe with negative curvature. If you've ever seen an M.C. Escher drawing of interlocking bats or angels within a circle where they get infinitely smaller as they approach the edge, that is a 2D representation of ADS space. The boundary is infinitely far away from the center, yet it encloses a finite volume.
Okay, so he has this negatively curved 3D bulk space.
Maldacena proved that the complex fluctuating force of gravity inside that 3D bulk is mathematically identical to a conformal field theory, a CFT, which is a quantum theory without gravity living purely on the 2D boundary of that space. Every single event, particle, and gravitational wave inside the 3D universe has a perfect, corresponding quantum twin on the 2D boundary.
That is staggering. It means gravity might just be an illusion produced by quantum math happening on a lower dimensional boundary. But how does this dictionary help us save my diary from the black hole?
To save the diary, we needed to know exactly how the boundary encodes the bulk. How does a flat surface create 3D space? The breakthrough came with the Ryu-Takayanagi, or RT, formula. This formula provided the exact translation mechanism, and it all comes down to quantum entanglement.
Entanglement. This is what Einstein called spooky action at a distance. When two quantum particles become so deeply linked that measuring the state of one instantly determines the state of the other, no matter how many light years separate them.
Yes. The RT formula showed that the amount of quantum entanglement between different regions on the 2D boundary directly determines the physical area of surfaces inside the 3D bulk.
Wait, let me make sure I'm following.
Oh.
The strength of the invisible, spooky connection between particles on the edge dictates the actual physical geometry, the literal distance on the inside.
Yes. Physicists began to realize that quantum entanglement is the literal thread that stitches space-time together. There is a concept called ER equals EPR, proposed by Susskind and Mendocino. It suggests that every time two particles are entangled, they are connected by a microscopic, incredibly thin wormhole in the fabric of space-time. If you sever the entanglement, space tears apart. Entanglement builds geometry.
If we take that a step further and apply it back to our evaporating black hole, what is happening to the entanglement of my diary?
To answer that, physicist Don Page modeled the evaporation process. He predicted what we now call the Page curve. Unitarity demands that information is conserved. So, as the black hole starts evaporating, emitting random Hawking radiation, the entanglement entropy, the amount of messy, hidden quantum connections between the inside of the black hole and the outside radiation, must go up.
The radiation is entangled with the particles that fell in. So as more radiation escapes, the entanglement grows.
Exactly. But Page realized that if the black hole eventually disappears completely and the information is somehow perfectly preserved in the escaping radiation, the final state of that radiation must be pure. It cannot be entangled with anything else because there is nothing left to be entangled with.
So the entanglement has to eventually drop back down to zero.
Yes, the Page curve shows the entanglement rising, hitting a peak known as the Page time, and then smoothly decreasing back to zero as the black hole finishes evaporating.
But Hawking's calculations said the entropy just keeps rising forever, straight off the chart. So how does the modern holographic dictionary force the math to follow the Page curve and save the diary?
Through the most mind-bending revelation of the last decade, the island formula and quantum extremal surfaces.
Let's unpack this carefully. What is an island inside a black hole?
Our sources detail this profoundly. Imagine the black hole evaporating. It hits the Page time. At this point, the black hole has emitted a massive amount of Hawking radiation, and that radiation is deeply, intensely entangled with the matter still trapped inside the black hole.
So the diary is still inside, entangled with the radiation far away.
The entanglement becomes so dense, so overwhelming, that the geometry of spacetime itself undergoes a radical phase transition. According to the RT formula, because entanglement builds geometry, the massive entanglement effectively forces a specific region deep inside the black hole's event horizon to mathematically connect the radiation far outside.
This region inside is the island.
Yes, and the mathematics of quantum extremal surfaces dictate that once this island forms, the information contained within that island is no longer exclusively inside the black hole. It is effectively mathematically encoded in the quantum state of the Hawking radiation light years away.
Okay, my brain is stretching. Are you saying that if my diary falls into the island region deep inside the black hole, I don't actually have to go into the black hole to read it?
That is exactly what the math suggests. The interior geometry of the black hole is secretly encoded in the exterior quantum entanglement of the radiation. Through a massively complex quantum computation on the escaping Hawking radiation, you could, theoretically, perfectly reconstruct the diary.
It is entirely non-local.
It is a radical destruction of our concept of locality. We like to think things are either here or there, but the holographic principle reveals that through intense entanglement, here can also be there. The information was never destroyed, it was just wildly redistributed and encoded into the geometric entanglement of the universe.
Let's just pause and take a long breath, because that is a monumental amount of reality-breaking physics to process. We've journeyed from the physical reality of antimatter falling downward into the mathematical terror of runaway negative mass billiard balls. We watch the quantum vacuum rebel by generating localized negative energy, only to be heavily policed by the average null energy condition.
And we just untangled the black hole information paradox, discovering that the deeply hidden interior of an event horizon is secretly projected onto the escaping radiation outside.
It sets up our final section perfectly, reimagining the universe.
Yeah.
Because if the interior of a black hole is a holographic projection and space-time geometry is just a web of quantum entanglement, what else could be hiding in the dark? Could this complex, non-local geometry be where our band negative mass actually lives? Or is the entire cosmos hiding a backside?
We are going to look at two highly radical, deeply paradigm-shifting theoretical frameworks from our sources. These theories attempt to solve some of our biggest cosmic mysteries by bringing negative mass back to the table, but doing so in a way that respects the complex geometric rules we've established.
Let's look at Theory 1, unitary time transformation in black holes. I love this one because it directly ties our black hole paradoxes back to our runaway billiard balls. How does it work?
This theory proposes a radical solution to the singularity at the center of a black hole. Classical theorems developed by Roger Penrose state that if gravity always pulls inward and energy is always positive, the matter inside a black hole must inevitably collapse into an infinitely dense point, a singularity where math ceases to function.
But this theory suggests gravity doesn't always pull inward.
It suggests that the event horizon isn't just a point of no return for light. It acts as a transformative boundary where matter undergoes a unitary parity time, or PT, transformation.
Let's break down a PT transformation. Parity is spatial. It's like looking in a mirror, flipping left and right, up and down. And time is literally reversing the flow of time. Time runs backward.
Exactly. And to understand the physical implications of time running backward, we have to look at the Feynman-Stueckelberg interpretation of quantum mechanics. Brilliant physicists Richard Feynman and Ernst Stueckelberg realized a profound mathematical equivalence.
What was it?
They realized that mathematically, a particle with normal positive energy moving backward in time is entirely indistinguishable from a particle with negative energy moving forward in time.
Oh, yeah. This links perfectly back to the Dirac sea.
Yes. A positron antimatter can be mathematically treated as a normal electron that has simply had its timeline reversed.
So if we apply this to the black hole, this theory posits that as normal, positive mass matter, like the collapsing star, crosses the intense gravitational threshold of the event horizon, the extreme curvature forces a PT transformation. Time effectively reverses for the infalling matter relative to the outside universe.
And because of the Feynman-Stueckelberg equivalence, if the matter is moving backward in time, it transforms into negative mass and negative energy.
The matter inside the black hole turns into our red billiard balls.
Exactly.
But wait, if it turns into negative mass, that means its active gravitational mass becomes negative. It no longer creates a gravity, well, it creates a gravity hill.
Right.
It pushes.
And that is the staggering brilliance of the theory. The moment the collapsing star crosses the horizon and turns into negative mass, it becomes gravitationally repulsive internally. The core of the black hole vehemently pushes outward against its own collapse.
It acts as an anti-gravity brake.
This internal repulsion entirely halts the collapse. It completely avoids the creation of an infinitely dense singularity. The matter just settles into a dense, repulsive core of negative mass. It violates the Penrose energy conditions, but only locally, safely hidden behind the horizon.
But if the inside of a black hole is a giant repulsive gravity hill, how does the outside universe not notice?
Yeah.
Why doesn't this negative mass push away the orbiting planets and stars, causing that terrifying runaway Bondi paradox with the rest of the galaxy?
Because of the absolute one-way nature of the event horizon, the negative mass is causally disconnected from the outside universe. Its repulsive gravitational waves cannot travel faster than light, which means they cannot escape the event horizon.
It's totally trapped.
It is entirely trapped. The outside universe only feels the original positive space-time curvature of the star that collapsed to form the black hole in the first place. The black hole acts as a perfect cosmic quarantine zone for broken physics and negative mass.
A quarantine zone for broken physics. That is so elegant. It solves the singularity, it hides the negative mass, and it perfectly balances the cosmic ledger. But if that isn't weird enough, let's scale the weirdness up from a single black hole to the entirety of space itself. Theory 2 from our sources, the Janus cosmological model.
This model, pioneered by French physicist Jean-Pierre Petit, takes the idea of negative mass and attempts to solve the runaway paradox without locking it inside a black hole. It does it by fundamentally redefining the geometric shape of the universe itself.
It's a biometric model. Let's unpack what biometric means.
In standard general relativity, space-time is described by a single metric, a single mathematical ruler that measures distances and times for everything in the universe. Imagine space-time as a single continuous sheet of rubber.
And if I put normal positive mass on it, like a bowling ball, it pulls the rubber down into a cone. A gravity well, everything rolls toward it. That is gravity as we know it.
And that is our side of the universe, the positive sector. But what if we introduce negative mass to this single sheet?
The classical view says it pushes the rubber up, creating a gravity hill. And that leads to the runaway billiard balls, because the hill chases the well.
Right. But the Janus model proposes that space-time doesn't have just one metric. It has two coupled metrics. Instead of a single sheet, imagine space-time has two sides, a front side and a back side. Two distinct parallel geometric pathways interwoven into the same cosmic fabric.
So positive mass lives on the front side, and negative mass lives on the back side.
Exactly. Now, when positive mass warps its metric, it creates that familiar gravity well, technically called a Poisson. But when negative mass warps its metric on the backside, it doesn't just push up, it creates a geometry of constant negative curvature.
I try to picture negative curvature. The only thing that comes to mind is a saddle, or honestly, a Pringles potato chip.
The Pringles chip is actually the perfect topological analogy. It curves up in one direction and down in the other. It is a negacone. The Janus model mathematically suggests that positive mass particles travel along the posicone geometry, and negative mass particles travel along the negacone geometry. They are two entirely different families of geodesics.
So how does separating them onto the front and back of the universe solve the Bondi runaway paradox?
Because the biometric nature of space modifies the rules of gravitational interaction. Within their own metric, things behave normally. Positive mass attracts positive mass, and crucially, in their own sector, negative mass attracts negative mass.
Wait, really? The red billiard balls attract each other?
Yes. On the backside of the universe, negative mass clumps together. It forms its own dark stars, its own invisible galaxies, completely stable.
But how do the front side and the back side interact with each other?
They interact purely through gravity, but the interaction across the biometric divide is entirely repulsive. Positive mass repels negative mass, and negative mass repels positive mass. They mutually push each other away.
Ugh, that instantly kills the paradox. The blue ball pushes the red ball away, and the red ball pushes the blue ball away. They just repel each other and drift apart. No infinite chasing, no runaway acceleration. The universe is safe.
The paradox vanishes. And the implications of this model are absolutely staggering when you apply them to observational cosmology, specifically to the greatest unsolved mystery in astrophysics, dark matter.
Dark matter, the invisible substance that supposedly makes up 85% of the mass in the universe. We can't see it, we can't touch it, but we observe its gravitational pull holding rotating galaxies together so they don't fly apart.
For decades, the mainstream consensus has assumed dark matter is some undiscovered, weakly interacting positive mass particle floating around in our own sector. But despite billions of dollars and massive underground detectors, we have never found a single particle.
So the Janus model offers an alternative.
A brilliant alternative. It asks, what if the gravitational effects we attribute to an invisible, positive dark matter are actually the result of massive clusters of negative mass living on the backside of the universe?
If they're on the backside, we could never see them with telescopes because they don't interact with our light.
Exactly. We would only feel their gravity. But remember, the rule. The interaction across sectors is repulsive. So a massive invisible cluster of negative mass on the backside would push against our space, creating a repulsive gravitational pressure.
It would act like a divergent lens.
Yeah.
Instead of pulling light in and magnifying it, it pushes light away and distorts it.
Precisely. And when cosmologists map the cosmic microwave background radiation and the distribution of galaxies, they rely heavily on gravitational lensing. The Janus model proponents argue that if you reinterpret that astronomical data, assuming divergent gravitational lensing from negative masses pushing from the backside, rather than convergent lensing from positive dark matter pulling from the front side, the mathematics align beautifully.
That is just, it completely flips our perspective. It means we aren't looking out into a vast empty space filled with invisible heavy particles acting as galactic glue. We are looking at the invisible pressure from a twin universe pushing against our own. It is an invisible corset shaping the galaxies into the massive, filament-like web structures we observe.
It is a radical reimagining of cosmology. These theories, the unitary PT transformation in black holes, and the biometric Janus model, they push the absolute limits of human imagination. They show us that decoding the dark isn't merely a matter of building a slightly larger particle collider to find a slightly heavier quark.
It is about fundamentally, conceptually rethinking the topology, the geometry, and the very fabric of reality itself. It requires a profound flexibility of mind. And I hope as you've been listening to us tonight, relaxing by the fire and letting these immense concepts wash over you, that you've felt that mental flexibility stretch.
It is a deeply humbling and yet deeply inspiring experience to realize just how much of the universe is not only unknown, but currently entirely invisible to our classical intuition.
Let's summarize the immense journey we've been on. We started anchored in the physical reality of the ALPHAG experiment, marveling at the engineering required to watch antimatter fall predictably downward. We confirmed that the Dirac sees negative energy bubble still obeys the normal rules of gravity.
We then journeyed into the pure mathematical terror of true negative mass, watching runaway billiard balls chase each other toward an infinite horizon, only to be stopped by the rigid classical guardrails of general relativity's energy conditions.
But we watched the quantum vacuum rebel. We saw the Casimir effect generate localized pockets of true negative energy, breaking the classical rules, only to be saved by the cosmic overdraft protection of the average null energy condition, enforcing topological censorship to prevent wormholes.
We waded into the cage matched the black hole information paradox. We explored how the holographic principle and the Ryu-Takayanagi formula revealed that space-time is stitched together by quantum entanglement, allowing the deeply hidden interior island of an event horizon to be secretly, non-locally projected onto the escaping Hawking radiation.
And finally, we peered into the radical frontiers of cosmology. We saw how a backward-flowing arrow of time could turn matter into a repulsive negative mass core, halting a black hole singularity. And we explored the biometric Pringles chip geometry of the Janus universe, where dark matter might just be the invisible repulsive pressure of a bustling twin universe on the backside of space-time.
It is a true testament to the power of theoretical physics to map the unseeable. And as we wind down this deep dive, I want to leave you with a final thought to ponder while you relax tonight. Something to mull over as you step outside and look up at the night sky.
What's the thought?
If the holographic principle tells us that the entire incredibly complex 3D universe we experience might just be a projection from a lower dimensional boundary, and the Janus model tells us there might literally be a geometric backside to the fabric of space, what if the dark, seemingly empty voids you see between the stars aren't empty at all?
That is a hauntingly beautiful concept.
What if those pitch-black regions of space are just the silhouettes, the repulsive gravitational shadows of a massive, bustling, negative universe existing right on the other side of the glass? A twin universe we can intimately feel but never ever touch.
That is exactly the kind of profound thought to drift off to. If you enjoyed decoding the dark with us today and expanding your cosmic horizons, please take a moment to like and subscribe to the channel. It really helps us keep diving deep into the profound mysteries of the cosmos, bringing these incredible concepts directly to you.
Keep questioning the reality around you. The universe is far stranger, far more deeply interwoven, and far more beautiful than our everyday intuition allows.
Until next time, stay curious, stay relaxed, and keep looking deeper. Good night.